who will talk about pushing the frontiers of quantum simulation with trapped ion quantum computers.
Yeah, thank you for that introduction. So I'm Mike Mills. I work at Quantinuum, and specifically, I'm an experimental physicist, and I kind of helped build the H2 system. And so we were lucky enough to have a lot of really brilliant people come up with some really cool applications and demonstrations to run on the machine. And so today I have the pleasure of sharing a number of those demonstrations with you. And so I'll briefly pull up our hardware roadmap at Quantinuum. And these first two purple ones are the existing commercial devices, the H1 and H2 machines. We're planning on releasing Helios soon this year, and so we're looking forward to that. But all the demonstrations I'll share with you today were done on the H2 mainly, and some on the H1 devices. And so the way that the H2 machine works is it has this racetrack geometry, just kind of an oval here. And so on the bottom, you can see a little video of some ions running around this racetrack. And in the H2 machine, we have 4 gating regions, or gate zones, shown as pink circles here. And so if we wanted to run some kind of arbitrary quantum circuit, maybe the first instruction is to perform 2-qubit gates with all qubits kind of next to their gating partner already. And so the way we would implement that is we would do 4 2-qubit gates in parallel on these qubits already in the gating regions. And then we can rotate all the qubits, transport them clockwise around the trap until a new batch of qubits are in the gating regions. And then we can perform the 2-qubit gates on those, and then shift again, gate, shift, gate, so on and so forth, until all 56 qubits have been gated. And then what we can do is we can look ahead in the circuit and find out what the next instruction is going to be. And so let's make an assumption that the top right circle is a visual representation of the next set of gate pairings, which were kind of arbitrarily randomly chosen. And so now qubits are not next to their gating partners, and so we need to rearrange all of the qubits so that they are, so that we can do another round of this gating. And so in order to rearrange the qubits so they all get next to their gating partners, we rely on a few ways to physically move these ions around. And so what we do is we basically combine 2 qubits so that they're next to each other, and then we can physically swap them around each other, and then split them and shift them around, and then do another round of combine, swap, split, so on and so forth, until we've achieved the desired ordering. This is essentially a 1D sorting algorithm, and so it's relatively inefficient as you scale to larger and larger systems. And so in the future, we're going to move towards other techniques, but in this trap, this is kind of what we use to set the ordering. And then once we have them ordered, we can do this gating, shift, gate, shift, gate, shift, and then so on and so forth until the end of the circuit. And there's a few nice features that we have on Quantinuum hardware. So we have low error rates in general. We have all-to-all connectivity that I just showed you we can implement through ion transport. And then we also have mid-circuit measurement and reset. And we can do conditional logic based on the results of these mid-circuit measures. We can do real-time decoding in a circuit. And we could actually then reset one of those qubits and then reuse it later on in the circuit. And so if you put all these things together, essentially it gives us a nice little playground where we can do a wide variety of different applications and demonstrations. And additionally, we can test a lot of different exotic QEC codes that are, say, non-local and benefit from all-to-all connectivity. And so one way to benchmark the performance of a quantum computer is using quantum volume, which essentially answers the question of how many qubits can you control with some threshold level of fidelity and control. And just a couple months ago, we're happy to announce that we've achieved a quantum volume of 2 to the 23, which is about 8 million. And this one is kind of special for us because back in mid-2020, if you see the little blue circle there, we actually made a promise to improve our performance in quantum volume by 10 times every year for 5 years. And so 2 to the 23 it takes us to the end of that commitment, actually. And so I think it's really cool to see that we've been, as we're scaling up the number of qubits we have from 6 to 10 to 12 to 20 to 32 to 56, the system sizes are getting bigger, but the error rates are going down rather than staying the same or getting worse. And so that's a good sign for us. And so we're excited to see what the next 5 years brings as well. And so with the H2 device, there's 56 qubits, and so 2 to the 56 is a pretty big number. And so maybe we can do something kind of at the limit, or maybe slightly beyond the range of classical computers. And so maybe the first step is we want to do some demonstration of quantum advantage. And so like similar demonstrations, we rely on random quantum circuits and to do these random circuit sampling problems. And so most of us are familiar with this, but in case you're not, very simply put, what we can do is we can perform some random circuit on our quantum computer and then measure the result. We'll get some, for n qubits, we get n zeros or ones out of the measurement. And there are 2 to the n possible measurements that we could have made, or I guess 2 to the n possible results of that measurement. And then if we assume it's a moderately simple program, so we can run it on a classical computer, we could do that and figure out what the probability of all those states should be if we're running this perfectly on our quantum computer. And then we could make this histogram of the probabilities of different bit strings to occur. And so with 2 to the n states, the average probability will be 1 over 2 to the n. However, some states should occur more often than other states. And so if we have a good quantum computer, we should be more likely to sample the the bit strings that correspond to probabilities that are above average. If we have a bad noisy quantum computer, we'll just kind of get random bit strings, and some will be above that line and some will be below it. And so you could imagine playing a simple game of running one instance of this random circuit on your quantum computer and getting the bit string out of the measurement. Then you go look up what the probability of that bit string should have been. And let's say it was above that black line shown. Then you put that result in a good bucket. And if it was below that line, then you put that result in a bad bucket. You repeat this, say, 100 times, and then you count how many results you have in the good bucket and the bad bucket. If your quantum computer is noisy, you'll have about half and half in each bucket. And if your quantum computer is good, you'll have more results in the good bucket than the bad. And that's a very simple qualitative explanation of how we can compute how good a quantum computer is at this random circuit sampling. And so on our devices, we have some advantages. Mainly, the all-to-all connectivity lets us run less deep circuits and still get just as much complexity as a deeper circuit would be if you only had 2D connectivity. And so these plots show essentially the maximum complexity in different colors up to black versus the number of qubits on the x-axis and the depth you'd have to run on the y-axis. And on the left is if you have all-to-all connectivity, basically about a depth 10 circuit is as deep as you need to go. And as you scale up to more qubits, you wouldn't need to run a deeper circuit in order to reach the same kind of complexity relatively. Whereas if you only have nearest neighbor connectivity, if you go to more qubits, you have to run deeper circuits, which leads to more gates and lower circuit fidelity. And so this fact enables us to perform these random circuit sampling experiments with very high fidelity. And so at 56 qubits, it's not as complex of a circuit as some of these really nice results from Google. And here I don't even have the results from Willow on there, which is well farther to the right, but still at a lower fidelity. And so those are certainly more complicated circuits. There's no questioning that. But we want to leverage the high fidelity that we have for these in order to perform maybe something useful. And so we can demonstrate that we can do something that's kind of complicated. And so maybe more importantly, we want to ask, can we do something that's useful that also could not be done classically? And there are 2 examples where I think we, by at least some metric or some definition of this usefulness, can say that we've done that. And the first example is using these random circuits to generate random numbers. And so, there's a market for random numbers, from encryption or, putting random seeds into important simulations. But basically, people buy random numbers. And so there is a market for this. And of course, being quantum, you can generate truly random numbers, which is, valuable. So it basically is not easy to be, hacked or, figured out how you get the random numbers. And we actually, we do this. I mean, we've been doing it for the past few years, where we, do some simple quantum circuit and measure the results and feed it back to customers. But that requires that the customer actually believes that we're running this on a quantum computer and not just kind of, generating it on our laptop and sending them the results. This protocol, which was proposed by Shihan Hung and Scott Aronson, kind of circumvents that in a way that we could not really be spoofing in any way on a classical computer. And so we actually performed this protocol in collaboration with JP Morgan Chase. And essentially how it worked is that JPMC would submit a random circuit to us, and at the same time they submitted it, they would start a stopwatch. And then we would receive that job, run on our quantum computer, measure the results, send the results back to them, and then as soon as they got the results, they would stop their stopwatch. They did this a bunch of times, and on average, that circuit runtime was about 2 seconds on the H2 device, and that includes communication overheads. And then after the fact, once they had all the results, they spot checked a subset of these on the world's most powerful supercomputer, and found that it took 100 seconds to get the answer. And they could also, since they spot checked some of them, see how well we did and see if we had a good fidelity and we're actually returning good quantum random results and not just any garbage data that's fast. And so basically with a high level of confidence, they could guarantee that we were actually running this on a quantum computer and giving them real random numbers based on the speed and the fidelity that we were able to do so. And so we did this with 30,000 circuits in total, and with some sort of calculation based on what the fidelity was and the speed relative to the most powerful computer in the world and what level of confidence you wanted to have, ended up getting 70,000 bits of entropy. And so if you do the math, that's about 1 bit per second, which is not very commercially valuable. And so there's certainly more work that could be done to make this a valuable thing. But it's kind of cool because we're actually generating something that you can sell for dollars and cents using a quantum computer that you couldn't have done elsewhere. And so the second example that I have is what we heard about on Monday, where we simulated the dynamics of quantum magnetism. And so I won't go over all the details again since Ellie explained it so well. But just to refresh your minds, what we did is we simulated the dynamics of a 7x8 2D transverse field Ising model using trotterization. And so since we were doing this trotterization, we had this kind of Goldilocks problem, where if we had large time steps, there wouldn't be a lot of hardware noise from the gates, but we would have a large discretization error. And so that's kind of similar to if you had some image that doesn't have a lot of pixels. And then conversely, if we had really small time steps, the discretization error would be small, but there would be a lot of hardware noise. And so maybe you could imagine that there would be a good image if it weren't so noisy. And so we had to find some kind of middle ground where there's a tolerable amount of hardware noise, but you have a reasonably good resolution. And when we did this, we found that for some range of parameters, we could observe this pre-thermalization phenomenon in a regime where all classical methods that we know about broke down. And so we think we were able to observe some dynamics of this system that we couldn't have done otherwise. And so that's a really good result. And a couple of the things we had kind of going for us in this experiment was, one, we had low physical errors. And so we have native arbitrary angle ZZ gates. And actually, the lower the angle is, the lower the error we achieve is. And so the average error in this experiment was 6 × 10⁻⁴. And then also, we ended up being kind of more robust to errors than we initially thought we would be because of this kind of error dissipation thing. And then finally, we leveraged error mitigation to further improve our results. And so we've got a couple of demonstrations with you could at least interpret somehow as practical quantum advantage. And so that's a really exciting result. And so what are we kind of looking forward to that might fall into this for near-term devices? And one particular thing we're excited about is looking at the Fermi-Hubbard model on our digital quantum computers. And to that end, we performed some experiments on the H2 device that were not beyond the classical limits, but show some promise. And so, as we've heard many times this week, this is an important model to solve, and a lot of effort has gone to building analog quantum simulators. And eventually, QEC may allow digital quantum computers to outperform analog quantum simulators. So far, though, digital quantum computers have lagged behind the performance of analog simulators. And these digital quantum computer experiments have been limited to quasi-1D models, which don't scale very favorably with system size. And in this work, we demonstrate a compact encoding that has some scaling advantages over the standard Jordan-Wigner approach. And so in general, to solve this problem on a quantum computer, the first step is maybe to encode the fermions into qubits using some method. Here I'm showing Jordan-Wigner and compact encoding. And then when you have it in terms of qubits, you can run it on your favorite quantum computer. And so for me, that means getting a bunch of ions together and zapping them with some lasers. And the different encodings, in the Jordan-Wigner, basically, you unravel the material into a 1D chain. Whereas with this compact encoding, you embed the material into a larger topologically ordered system. And you store the fermionic exchange statistics in a local way by implementing these ancilla qubits shown in red on the bottom plot. And so to get into a little bit more detail, for this Jordan-Wigner approach, we have this kind of snaking pattern in 1D. And so hopping terms, for these two sites shown, require kind of doing a series of gates in order to implement. And so especially as the system size grows larger and larger, this is kind of inefficient. And instead, if we store the exchange statistics in these ancilla qubits, all the qubit hopping operators have weight 3 instead. And then additionally, we have these shaded gray stabilizers that we can utilize that we set to +1 and should be conserved as +1 throughout the evolution we considered in this work. And one other detail that I won't get into is we implemented this corner hopping compilation strategy that allowed us to further reduce the number of 2-qubit gates that we need. And we performed this experiment on the H2 system on both a 4x4 lattice and a 6x6 lattice, shown in the two plots on the top right. And what you can see is that for the 4x4 lattice, the Jordan-Wigner and compact encoding performed comparably. However, in the 6x6 lattice, you can see that the orange compact encoding was a little bit closer to that noiseless simulation. And we can see that in the bottom plot with this SNR, where for system size 6x6, the orange is kind of outside of error bars of the blue. And we think this is primarily due to the reduced number of 2-qubit gates that we had to do for this compact encoding for the 6x6 system size. And generally, as we scale system size, you can see on this plot on the bottom left that the number of gates that are required are lower for this compact encoding. And implementing this corner hopping strategy allowed us to reduce that kind of crossover point from 10 by 10 to about 6 by 6 or so, or theoretically close to 4 by 4. And additionally, we can perform some error mitigation by leveraging some of the information about the system. And so for one, we can do what we call N filtering, which basically post-selects on only shots that preserve the particle number. And then additionally, we can use these stabilizers to do post-selection as well, and only choose results that had all the stabilizers measured as +1. And if we combine those two, we can do what we call global filtering, which we can see on the right plot here, allows us to take that raw data and much better reproduce the noiseless simulation. However, it comes at a cost, of course, so it improves the data, but it doesn't really scale well, because if you do global filtering, then you start growing your system size. If you get a single error, you have to throw out all the data. And so it doesn't really scale well, and it's relatively wasteful. And so in the limit of the large system sizes, any single error would only really have we'll only really be able to affect a certain subset of bits based on essentially a light cone propagating from that erroneous bit. And so we don't necessarily have to discard all of the shots. And so if we use this local filtering, then we only discard shots locally around that faulty stabilizer. And we determine the location of the errors with these stabilizer measurements. And so if those errors occurred, say, just before an energy measurement, then the unaffected bits could still be used. And so this reduces the amount of data that we have to throw away. And it also kind of makes it a little bit more favorable to scale up in terms of system size. And we can kind of see this graphically in these top two plots. And so the top plot on the left shows, not really much of a plot, it's just a box, but it shows the regime where global filtering is applicable. Basically, you can't have any errors in your system. Whereas the plot on the top right shows the regime at which local filtering could be useful, where instead of relying on no errors at all, basically what you need is the density of your errors to be relatively small. And then on the bottom right, we show two useful pieces of information in one here. The data points with error bars show essentially the quality of the data, and so being closer to the black line is better. And then the bars behind them show how many of the bits we were able to use in terms of percentage. And so you can see for the raw data, of course, we were able to use 100% of the bits. And then we can see that the best filtering that we saw was with some of this global filtering. However, we lost a lot of the bits and the data from that. Whereas this local filtering offered a pretty significant improvement in the performance, where we were still able to keep somewhere around 80% of those bits. And so it'll also be more scalable to future. And so some of the outlook we had from this work, we only did a 6x6 grid, and so it could be computed classically. However, if we extract the SNR that we got here to a system size of about 10 by 10, we'd expect that we might be able to have a signal of about 20% for 20 Trotter steps. And it may be recoverable by error mitigation. And this system size would fall into a regime that is challenging for classical methods. And so this could be a potential candidate for exciting research on near-term devices. And so this also suggests that we could do these simulations on a noisy digital quantum computer without error correction. And as long as the gate and memory errors deteriorate only mildly when we scale the system, but hopefully they actually get better as well. And so we've demonstrated that we have several methods that we think can perform some useful calculations on existing near-term noisy digital quantum computers. But of course, in the long run, we want to move towards a fault-tolerant, large-scale QEC calculations. And so to that end, I want to share some of the demonstrations, kind of a snapshot in time of what we've been doing with QEC in mind. And so the first demonstration I want to talk about is a collaboration we did with Microsoft, where they looked at logical Bell state preparation using two different codes, the 713 Steen code and a 1224 Carbon code that they developed. And so we can see the performance of a few different cases on these bar charts on the right. And so the 713 Steen code, you can correct one error, or if you wanted to not try and correct it, you could still detect it and then not do anything about it. And what we see is that actually, performing the correction improves the results from the physical error, but the detection actually performed even better when we just tossed out the data instead of trying to correct it. And then for the 1224 Carbon code, again, doing error correction only improved the error rate from the physical. And then since it's distance 4, you can correct one error and detect a second error. And so the label there is error corrected and detected rather than just detected. And one thing that really struck me with this result is how high performance the error detection was. And so in both of these codes, in both of these experiments, we actually did over 10,000 trials with error detection and measured exactly 0 errors. And so this was running on the machine probably for several hours each. And so there were no sneaky errors that came in that time, which was pretty cool to see. And the other thing that struck me was the relatively small amount of data we actually had to throw away by this error detection. And so we can see that by comparing the pre-accepted column and the post-accepted column. And so if you look at the 1224 carbon code here, the pre-accepted versus post-accepted, we only had to throw out 70-something shots out of 15,000 total. And we were able to get such a drastic improvement in the performance. And so I think, this, at least to me, this points to maybe in near-term devices, if our goal is not to build a fully fault-tolerant device, but rather do something useful with something in the next few years, maybe we should, be more tolerant of non-fault-tolerant methods and and maybe utilize this error detection more. The next demonstration I wanted to share, it was actually inspired by an IARPA program, ELQ, Entangled Logical Qubits. That was a 4-year program aimed to achieve teleportation of logical states with 95% fidelity. We actually applied for and did not get this program, but we decided to try our hands at it anyways. And less than a year in, we did this, and the logical teleportation rate was less than 1% instead of less than 5%. And then in the year following, we actually made some hardware improvements, and so we wanted to see how the results would compare to the previous year. And actually, we saw something interesting. And we saw that our physical error rates improved by roughly 2 times, but we saw a 4 times improvement in our logical error rates. And additionally now, if you look at that 2025 data point, the orange logical teleportation data is significantly below the physical teleportation error rate. And so now about halfway through the timeline for this program, the target rate was 5%, and we're now at 0.18%. And then additionally, as I briefly mentioned earlier, the all-to-all connectivity that we have in our systems allows us to take advantage of some kind of more exotic QEC codes that require this high connectivity. And so I want to briefly talk about 2 of these codes. The first is this 3314 4D surface code. And this was actually, we had a summer intern a couple of years ago from UMD, and he actually came in and had this idea and ran it on the device and wrote a paper on this all in the short summer internship period. And so this was really cool, even just for that aspect of it. But this code is kind of nice in that it has a property known as single-shot QEC. And so usually QEC of code distance D would require about D rounds of syndrome measurement, whereas this would only require 1. And so as we move to very large distance codes, this could potentially offer some speed-ups for running the actual circuits, something like this at least. The second code I want to talk about on this slide is another collaboration with Microsoft, where we played around with the 1664 tesseract code, which is shown in this plot on the right. And so it's a 4D hypercube code. And we did a number of fun experiments with this. One thing that was kind of a fun little thing for me was that we made a 12 logical qubit GHZ state, and we did it with 99.9% fidelity, which was 22 times better than making a 12 qubit GHZ state with our physical qubits. And so I thought that was a pretty cool result. And the next thing I want to talk about is magic states. And so oftentimes the most challenging part for a fault-tolerant universal gate set is performing a non-Clifford gate, which is needed to do things that can't be classically simulated. And these are often done in a fault-tolerant way by creating special resource states known as magic states, which you could either fault-tolerantly prepare, or you could prepare in a noisy way and then distill it down to high quality. And as we're interested in these non-local exotic QEC codes that might offer some scaling advantage if we have this all-to-all connectivity, it's important to kind of do some work on these magic states because the preparation of magic states in these codes are not as well studied, and they have higher overhead costs compared to the state-of-the-art methods for surface and color codes. And so one demonstration we did towards looking at this magic state preparation was utilizing the 622 error detection code and then using 2 extra ancilla qubits for a check here. And that makes it a total of 8 physical qubits to prepare a magic state. And we were able to implement this scheme experimentally and observe a 7 × 10⁻⁵ magic state preparation error rate with about a 15% discard rate at a pretty low ratio of only 8 physical qubits per magic state. And we were actually able to then use one of these magic states to perform a fault-tolerant non-Clifford gate, the controlled Hadamard gate, and got a logical fidelity of 2.3 × 10⁻⁴, which is about 4 times better than our physical error rate. And so that in itself is a really exciting result. And so if we call this procedure level 1, then we can define some level 2 protocol, which is just the self-concatenation of that level 1 protocol, which would then produce 4 magic states in a 3644 code block and use 160 physical qubits. We didn't have 160 physical qubits, so we had to rely on simulations. And so doing some error modeling for this, we think that if we have a physical error rate of 10⁻⁵, that this level 2 protocol would produce magic state preparation infidelities about 5 × 10⁻⁻10 with an acceptance rate of 67%. And if we were able to further improve our physical error rates to 10⁻⁴, we think it would produce 3.6 × 10⁻⁴ magic state preparation infidelity with a 96% acceptance rate. And so this would be like a really high quality magic state, and it would only require 40 physical qubits per magic state and would run in depth 15. And so what we get out of that is a magic state factory with a small space-time footprint. And so one other way we can we can get high quality magic states is through a technique known as code switching. And so this was a collaboration with researchers at UC Davis. And so code switching is an alternative to magic state distillation. And in this approach, you start in a code that admits transversal non-Clifford gates, such as a T-gate. And then you switch to another code that admits a complementary set of transversal gates. Oh. Okay. Yeah. So I guess this whatever 3D code is the 1513 QRM code, which is a 3D color code, and the bottom one is the 713 Steen code. And so imagine we're looking at that rather than bigger text. But we were able to actually perform this experiment, switching between these codes, and we were able to create a magic state with a preparation error of 5.1 × 10⁻⁴, which is better than our physical 2-qubit and spam errors. And we had about a 17% discard rate, and this gave us 28 physical qubits per magic state. And so since we have 56 qubits in the trap, we could actually make 2 copies of this magic state and then perform logical Bell basis measurements to certify the encoded state more efficiently. And if we compare this to previous work, the best previous work utilized post-selection and had about 8 × 10⁻⁴ error rates. And this work did not utilize post-selection and got an even better fidelity, which is exciting. And our QEC team is maybe a little too modest because they showed other people's post-selection work, but not ours. And so luckily I have no shame. And so if we include our post-selected fidelity as well, you can see that we actually reduced the error rate from 5 × 10⁻⁴ to 1.5 × 10⁻⁴, with really only a small overhead in the acceptance rate, just down from 82% to 81%. And so not that bad. And then another project I want to talk about is one with a collaboration between Princeton and NIST. And actually, Grace has a poster on this later today, and so I strongly urge you to go talk to her about this and get more of the details. And also, Michael Gullins is here this week as well, presenting on other work tomorrow. And so that makes at least 2 people in the audience who understand this work better than I do. But To give a brief overview of what we did on the experiment, we used a self-concatenated generalized Shor code with the NKD parameters shown as such, and then did a multi-tree state preparation with 0 ancilla overhead. And so for some parameter t, it really only required 2 to the t physical qubits. And then utilized a novel tensor network-based approximate decoder. And the simulation suggests that the state prep for this method would show threshold at about 9% for erasure errors. And then on the experiment, we have 56 qubits, and so the multiple of 2 we can get to is t to the 5 for 32 qubits. And then we can introduce heralded incoherent noise and coherent rotations to scale that error rate. And we actually observed this threshold, and then with low values of added error, observe this subthreshold behavior where higher code distance gives us lower error rates. And then lastly, if we put all these QEC techniques together and we utilize it to try and do some sort of simulation, we recently published this paper kind of doing an end-to-end pipeline for QEC to compute molecular energies. And so as a demo, we calculated the ground state of the H2 molecule, and so we like to call this project H2 on H2, using quantum phase estimation for qubits encoded in the 713 color code. And so these circuits that we ran contained 22 qubits, used about 2,200 physical t-qubit gates, 760 mid-circuit measures. And if we look at the plot on the right, the y-axis is essentially our hardware noise, and the x-axis is some precision parameter k. And so farther to the right means finer resolution, but it also means more gates and more hardware noise. And kind of maybe the key result here, we relied on both emulator data and hardware data. We saw the emulator and hardware matched pretty well. And if we do the no QEC versus the experiment, that's essentially what that is adding QEC gadgets in the middle. And what we find is that adding QEC gadgets in the middle of this circuit actually improves the results of the QPE for higher precision parameters where we have more gates, rather than making it worse, which is kind of exciting. And granted, we still had an error in the ground state energy estimation of 0.018 Hartree, which is bigger than the chemical precision, but as a demo of how to do QEC to calculate parameters, this was a nice demonstration. And so just again, real briefly, pop up this hardware roadmap. And so we're hard at work making this Helios device work, and we're hoping to release this commercially later this year. And I can't quite thank everyone and put their faces up, but to give you some idea of the work that went into this, I'll just flash up the different papers that went into this talk to give you some idea of how many authors there were and how many contributions there were. And last but not least, I'd like to thank the organizers and thank you for your time and welcome any questions.